Having looked now at several slicing models for computing volumes, we're going to generalize this to an area called volumes of revolution. Let's see how this works. Imagine the graph of y equals e to the negative x, so the exponential decay graph, shown here. And the solid, how do we get a volume out of a graph? What we're going to do is we're going to spin that shape, that graph, and we're going to use the x-axis as a boundary, x equals 0, and x equals 3 as a boundary. And we're going to spin that around. And if we did that, we would get this funnel type shape. It would be solid, and it would come from this exponential decay curve here. That's what we can see as the boundary, but just being spun around the x-axis. Having seen that, the challenge we'd like to investigate is how could we find the volume of this three-dimensional shape? We start in 2 dimensions, but through the spinning action, we generate a 3-dimensional solid, and we want to find the volume of that solid. Okay. Well, how can we find that volume? Well, we're going to take the same approach we have been taking up until now. We're going to imagine this whole volume, which is a crazy curved shape, and we're going to slice it. We're going to slice it into little thin slices, delta x width, delta x wide. And if we do that, what are we going to obtain? We're going to obtain little cylinders. If I cut here, I'm going to get a thin cylinder, delta x thick, and with a circle as a cross section. So we're going to get thin cylinders wherever we cut. As long as we cut perpendicular to the x-axis, because we're spinning around the x-axis, we're going to get a circular cross section with just a little thickness, delta x. Okay, so we've decided our first thing. How are we going to slice this shape? The next question is, what is the volume of a generic slice? So let's imagine cutting here, and we're spinning this, so we're going to have a shape like this. If we slice here, let's bring this out. Oops. Let's bring this out a little better. The shape we're going to get is a circle, and it's going to have a little thickness, delta x. Delta x is that thickness there. So if we take a generic slice and we want to find its volume, we know already one dimension, its thickness. The other dimension we want to know is the radius. The key thing here, though, is that the radius is equal to the y height, the y coordinate. If I know what the y coordinate is on this graph, that's also the distance between y equals 0 and the point, and so it's going to equal our y value. So if we want to find the volume of one slice, it's going to equal the area of the circle times the thickness. So 2 dimensions and a third dimension there. The area of the circle will be pi r squared. The thickness will be delta x. The radius is given by the y coordinate, so we could call that pi y squared if we liked, times delta x for the thickness. And our last challenge is to recognize that, well, y doesn't tell us very much if we're doing all these slices depending on the x coordinate. So we have to go from this y coordinate. How do we tie that back to x's? Well, we remember that this curve is defined by the exponential decay, y equals e to the negative x. So we take that. That's what defines this y coordinate. And so we replace the y with e to the negative x squared. Sorry, e to the negative x. And we replace the y with that, and the whole thing is squared. And now we have the volume of one slice. If I know what my x-coordinate is, my x-coordinate is out here close to 3, I will have a very small radius. I'll take that radius and square it, times pi to get an area. Area times delta x gives me a volume. If I had a very small x close to 0, I would plug my x into here, get a bigger radius, bigger area, and find the volume of that slice. And the integral is what's going to let us add up to get the total volume. It'll add up all those slices for us to get the total volume. Notice we just copy everything down exactly as is. The only thing that changes is the delta x becomes our traditional dx in the Leibniz notation. Last but not least, we just have to indicate where we're starting. This was given in the problem. It said the boundaries are x equals 0 and x equals 3. We're integrating with respect to x, so x and 0 and 3 are the locations of the first and last slices here. And that's it. That's our first extraction or derivation of an integral representing a volume obtained by revolving, that's the revolution, revolving the curve y equals negative x around some axis. The next step is simply to evaluate that, and that's fairly straightforward again. The only thing you have to remember is what do nested powers do? Well, the pi can come out front, but e to the negative x to the power 2, we get that by multiplying the exponents and keeping everything else the same. E to the negative x squared is the same as e to the negative 2x. Once we have that, we can simply evaluate what's the antiderivative of e to the negative 2x. Well, it's e to the negative 2x over negative 2. And we're going to evaluate that at 3 and 0. And so we get pi e to the negative 6x over 2 minus e to the 0 over 2, negative 2. And that works out to roughly approximately 1.57 cubic units. And so we have the integral being built by slicing volumes, finding the volumes of each slice as we go through this, and computing the overall value by plugging that slice volume into an integral form, using the integral to find the sum of those volumes with very, very thin delta x slices, and we obtain the final volume simply by evaluating the integral.